In a 1600 amp 480 volt service, the sizing of the bonding conductor for the bonding bushings is critical for ensuring electrical safety and compliance with the National Electrical Code, or NEC. The scenario described involves 4 electrical metallic tubing, or IMT, conduits, each containing 900 aluminum conductors, entering the main distribution panel, or MDP. A number 3/0 copper conductor is connected to the building steel and extends to the copper water service. A number 6 copper conductor connects to a ground rod. A number 1/0 copper conductor loops to the 4 bonding bushings, with all grounds and neutrals connected together. The specific question is whether the number 1/0 copper conductor used on the bushings is of legal size. According to the NEC, the equipment grounding conductor, or EG, must be sized according to Table 250.122. This table provides minimum sizes for equipment grounding conductors based on the rating of the overcurrent protective device protecting the circuit. In this case, the overcurrent protective device is the 1600 amp service disconnect. Referring to NEC Table 250.122, for a 1600 amp overcurrent device, the minimum size for copper equipment grounding conductor is number 3/0. The bonding bushings are used to ensure a low impedance path for fault current back to the source. This is crucial for the proper operation of overcurrent protective devices, such as circuit breakers or fuses, during a ground fault. The main purpose of bonding is to create an electrically conductive path that allows fault current to flow quickly and safely back to the source, thereby tripping the overcurrent device and clearing the fault. The bonding jumpers connected to the bonding bushings must be sized appropriately to handle the available fault current. Since the number 1/0 copper conductor is smaller than the minimum size required by NEC Table 250.122 for a 1600 amp service, it is not considered legally sized. The NEC mandates that the bonding jumper must be at least the size of the equipment grounding conductor specified in Table 250.122. Therefore, a number 3/0 copper conductor is required for the bonding bushings in this scenario. The connection to the building steel and the water pipe using a number 3/0 copper conductor serves as the main grounding electrode conductor, or GEC. This conductor connects the service equipment to the grounding electrode system, which includes the building steel, the water pipe, and the ground rod. The number 6 copper conductor connected to the ground rod provides an additional grounding electrode. The grounding electrode system must be properly installed and maintained to ensure a low impedance path to ground. The connection of all grounds and neutrals together at the service equipment is a standard practice. This connection ensures that the neutral conductor is properly grounded, providing a return path for normal current flow and a low impedance path for fault current. The main bonding jumper, or MBJ, is used to connect the ground and neutral conductor to the equipment grounding conductors at the service equipment. This connection is essential for establishing a solid ground reference and facilitating the operation of overcurrent protective devices. Now let's delve deeper into the specific NEC requirements that pertain to this situation. NEC Section 250.24. C addresses the grounding of the service neutral. It requires that the grounded conductor be connected to the grounding electrode conductor at the service equipment. This connection must be made using a main bonding jumper, which can be a wire, busbar, or other suitable conductor. The size of the main bonding jumper is determined by NEC Table 250.102. Seat 1, which is based on the size of the service entrance conductors. In this case, the service entrance conductors are the 4 sets of 900 aluminum conductors. To determine the equivalent copper size for these aluminum conductors, we can use NEC Table 310.16, which provides ampacity ratings for conductors. A 900 aluminum conductor typically has an ampacity of around 640 amps, depending on the insulation type and installation conditions. Since there are 4 such conductors in parallel, the total ampacity is 4 times 640, which equals 2560 amps. Based on this total ampacity, the equivalent copper conductor size would be larger than a number 3/0. Therefore, the main bonding jumper must be sized accordingly. NEC Section 250.66 provides requirements for the size of the grounding electrode conductor. The grounding electrode conductor connects the service equipment to the grounding electrode system. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in Table 250.66. For service entrance conductors larger than 1100 copper or 1750 aluminum, the grounding electrode conductor must be at least number 3/0 copper or 250 kcmil aluminum. The number 3/0 copper conductor connected to the building steel and the water pipe appears to meet this requirement, assuming the water pipe is a qualifying grounding electrode. NEC Section 250.104 addresses the bonding of metal water piping systems. It requires that metal water piping systems that are likely to become energized be bonded to the service equipment. This bonding connection must be made using a bonding jumper sized according to Table 250.102. C1. The number 3/0 copper conductor connected to the water pipe appears to satisfy this requirement, assuming it is properly connected and sized according to the applicable tables. NEC Section 250.52 specifies the requirements for grounding electrodes. It lists various types of grounding electrodes, including metal underground water pipes, building steel, and ground rods. Each type of grounding electrode has specific requirements for installation and sizing. The ground rod must be at least 8 feet long and must be driven into the ground so that at least 8 feet of its length is in contact with the soil. The number 6 copper conductor connected to the ground rod serves as a supplemental grounding electrode. While a single ground rod is typically not sufficient as the sole grounding electrode, it can be used in conjunction with other grounding electrodes, such as the building steel and the water pipe. The purpose of the supplemental grounding electrode is to improve the overall grounding system and provide additional protection against ground faults. It is important to note that the NEC is a minimum standard. In some cases, it may be necessary to exceed the minimum requirements to ensure adequate safety and performance. For example, in areas with high soil resistivity, it may be necessary to install additional ground rods or use other grounding techniques to achieve a low impedance ground. Similarly, in applications with sensitive electronic equipment, it may be necessary to use special grounding and bonding techniques to minimize electrical noise and interference. In summary, the number 1/0 copper conductor used for the bonding bushings in the 1600 amp 480 volt service is not of legal size. The NEC requires a minimum size of number 3/0 copper for the equipment grounding conductor and bonding jumpers in this application. The other grounding and bonding connections appear to be in compliance with the NEC, assuming they are properly installed and sized according to the applicable tables. It is crucial to consult the latest edition of the NEC and local electrical codes to ensure compliance with all applicable requirements. Additionally, it is recommended to consult with a qualified electrical engineer or inspector to ensure that the grounding and bonding system is properly designed and installed. Proper grounding and bonding are essential for electrical safety and the reliable operation of electrical equipment. Failure to comply with these requirements can result in electrical shock, fire, and equipment damage. It is important to take these requirements seriously and to ensure that all electrical work is performed by qualified professionals. Now, let's further elaborate on the importance of low impedance grounding paths. The term impedance encompasses both resistance and reactance. In AC circuits, reactance is the opposition to current flow due to inductance and capacitance. A low impedance ground path is crucial for facilitating the rapid clearing of ground faults. When a ground fault occurs, a large amount of current flows through the grounding system. If the impedance of the grounding path is too high, the fault current will be limited, and the overcurrent protective device may not trip quickly enough. This can result in a dangerous situation, where energized metal parts pose a shock hazard. A low impedance ground path ensures that the fault current is high enough to quickly trip the overcurrent device, thereby de-energizing the circuit and minimizing the risk of electrical shock or fire. The bonding bushings play a critical role in providing a low impedance path for fault current. They are used to bond metal enclosures such as conduit and equipment cabinets to the equipment grounding conductor. This bonding ensures that all metal parts are at the same electrical potential, minimizing the voltage difference between them and reducing the risk of electrical shock. The bonding jumpers connected to the bonding bushings must be sized appropriately to handle the available fault current. If the bonding jumpers are too small, they will introduce additional impedance into the grounding path, which can impede the flow of fault current. The NEC specifies the minimum size for bonding jumpers based on the size of the circuit conductors. However, in some cases, it may be necessary to use larger bonding jumpers to ensure a low impedance ground path. Another important aspect of grounding and bonding is the concept of equipotential bonding. Equipotential bonding involves connecting all metal parts in an area to the same electrical potential. This is typically achieved by bonding together all metal pipes, conduits, and equipment enclosures in the area. The purpose of equipotential bonding is to minimize voltage differences between metal parts, thereby reducing the risk of electrical shock. Equipotential bonding is particularly important in areas where people are likely to come into contact with metal parts, such as bathrooms, kitchens, and swimming pools. In these areas, even small voltage differences can pose a significant shock hazard. By bonding all metal parts together, the voltage differences are minimized and the risk of electrical shock is greatly reduced. Now let's discuss some common grounding and bonding mistakes. One common mistake is using undersized grounding conductors. As mentioned earlier, the NEC specifies the minimum size for grounding conductors based on the size of the circuit conductors. However, some electricians may mistakenly use smaller grounding conductors either to save money or because they are unaware of the NEC requirements. Using undersized grounding conductors can compromise the effectiveness of the grounding system and increase the risk of electrical shock or fire. Another common mistake is failing to properly bond metal enclosures. Metal enclosures, such as conduit and equipment cabinets, must be properly bonded to the equipment grounding conductor. This bonding ensures that the enclosures are at the same electrical potential as the grounding system. If the enclosures are not properly bonded, they can become energized during a ground fault, posing a shock hazard. A third common mistake is using improper grounding techniques. There are specific grounding techniques that must be used in certain situations. For example, isolated ground receptacles must be used in sensitive electronic equipment to minimize electrical noise and interference. Similarly, surge protective devices must be properly grounded to provide effective protection against voltage surges. Using improper grounding techniques can compromise the performance of the grounding system and increase the risk of equipment damage. In conclusion, grounding and bonding are essential for electrical safety and the reliable operation of electrical equipment. It is important to understand the NEC requirements for grounding and bonding and to follow these requirements carefully. If you are unsure about any aspect of grounding and bonding, it is best to consult with a qualified electrical engineer or inspector. By taking the time to properly ground and bond your electrical system, you can protect yourself, your family, and your property from the hazards of electricity. Remember, electricity is a powerful force, and it must be treated with respect. Proper grounding and bonding are the first line of defense against electrical hazards.